So the next talk is by Ilaria Ruffa, who is a postdoc at Cardiff University, and we go to slightly larger scales, so sub-kiloparsec scales at local radio galaxies.
Yeah, so hello everyone, good afternoon. Thank you very much for the introduction, and thanks to all the organizers for giving me the opportunity to talk today about some of the exciting results I've been obtaining in the last few years using ALMA observations on local radio galaxies. So let me start by briefly introducing the topic of this talk. I think we all agree on the fact that the Asian population can be really varied, but if we focus on the local universe, it is now widely accepted that we can distinguish two main Asian modes, differentiated by the dominant type of energetic output. We have radiative mode Asian on one hand and jet mode Asian on the other hand. In radiative mode Asian, the accretion occurs at high rates, and the dominant type of energetic output is in the form of the electromagnetic radiation released by the gas that is accreting onto the supermassive black hole. In jet mode Asian, the accretion occurs at low rates, and the dominant type of feedback is in kinetic form through the radio jets. And I will focus on this second Asian category, which in the local universe is typically associated to these radio galaxies called low excitation radio galaxies, which are a class of objects characterized by weak low ionization narrow emission lines in their optical spectra, moderate radioluminosities, mostly SR1 radiomorphologies, such as the prototypical LIRGs shown in this map, which is 3C31. They are typically hosted by very massive early type galaxies characterized by an old stellar population. So these objects are those typically occupying the high mass tip of the passive sequence in the optical color magnitude diagram shown here on the left. And for this reason, these objects have been typically believed for a long time to be essentially gas-poor red and dead galaxies. So the question is, why do we care about LIRGs? Mainly because they are numerically dominant in the local universe, but spatially resolved studies of these objects were very sparse so far, and therefore the Asian feedback loop still poorly understood. So for this reason, we started this project, the Southern Sample Project, consisting on the first systematic study of a volume-limited sample of 11 LIRGs in the southern sky, and the 11 targets are listed in this table. Our main aim was to mainly carry out a detailed investigation of the Asian feedback loop mapping different galaxy components. And to this aim, we acquired a huge data set spanning from VLA continuum and data H1 observations and going through optical continuum and IFU spectroscopy. But in particular today, of course, I'm going to talk about molecular gas observations obtained in the past few years using ALMA. So let me start presenting the general properties of the molecular gas. 9 targets, 9 of the 11 sample members have been observed during cycle 3 in CO221 with ALMA. 6 out of 9 objects have been detected in CO221, and here I show the mean velocity maps or moment 1 maps of the 6 CO detections. And as you can see, in all the cases, we detect rotating CO disks or rings with sizes spanning from a few hundreds of parsec to 10 kiloparsec in the case of NGC 612, and molecular gas masses ranging from 10 to the 7 to 10 to the 10 solar masses. So now the important information that we can extract from these detections is that rotating CO disks are very common in LERCs. And this is telling us an important information, which is that considerable amounts of cold gas are confined in the inner sub-kiloparsec scales of these objects, contrarily to what popularly believed for this kind of galaxies. We also carried out a detailed modeling of the CO kinematics using the KineMES tool, and here I show 4 examples, and for each target you can see on the left-hand side the observed velocity field, and on the right-hand side the modeled velocity field. And as you can see from these panels, in all the cases the gas kinematics appear to be reasonably well reproduced using simple axisymmetric models, assuming gas in purely circular motions. This is another piece of important information, mainly because this is telling us that the bulk of the gas is in ordered rotation, suggesting a possible link with the low accretion rates in layers, because of course, if the gas is in ordered rotation and stable orbits, it is also likely stable against the fragmentation. So this suggests indeed a link with the low accretion rates of layers. Nevertheless, we observe in all the cases signs of asymmetries or perturbations, and here I show 3 examples in which in all the cases you can see there are asymmetries, perturbations in the measure axis position velocity diagram that are not reproduced by our model, kinematic model overlaid here in Strian contours, and the asymmetries are also observed at corresponding positions in the mean velocity fields. And interestingly, for EC 1531 and NGC 3557, the asymmetries appear to be located along the path of the jet, indicated here as dashed arrow, suggesting possible cases of jet gas interactions, which have been already claimed for 3557 by other authors. But the take-home message that the thing that I would like to highlight from this analysis is that disturbed CO disks are not standard in local radio quiet early type galaxies, indicating that the gas reservoirs that we observed in these objects are likely a fundamental they have likely a fundamental role in the feeding feedback loops of LERCs. But let me now talk more in detail about jet ISM interactions, which is a really interesting piece of our work, mainly because it has been observed only very recently that expanding radio jets can have a huge impact on the ISM, also on sub-kiloparsec scales, and not only on tens of kiloparsec scales on the hot X-ray emitting atmospheres. And this observational finding is confirmed also by 3D, is supported by 3D hydrodynamical simulations showing that the jet ISM coupling on sub-kiloparsec scales is very sensitive to the jet gas relative orientation, jet power and age, and in particular, as shown in this in the snapshot on the right-hand side from the Mukherjee et al. Simulation, the coupling is maximized, is stronger for jets more inclined toward the plane of the gas distribution, and also when the jets are very young and with intermediate or low powers. Now, let me now focus on one of our targets, one of the targets in our sample, which is 3100. which turned out to be a good case for studying a jet ISM interaction on sub-kiloparsec scales. Now, 3100 is a lenticular, a nearby lenticular galaxy that you can appreciate here in this optical B-band map, characterized also by a patchy dust distribution that you can see here on this Bimini dust extinction map on the top right panel. Now, from the previous CO221 observations, what we observe in 3100 is this well-resolved CO221 ring-like structure extending up to 1.6 kiloparsec along the major axis and nicely cospatial with the central dust distribution. Another interesting feature, which then made us thinking on a possible jet-gas interaction in this object is that the CO distribution here in the bottom right panel is clearly disrupted around in a position which is coincident with the bend of the northern radiojet here overlaid in red contours from our 10 gigahertz JVLA observations. In addition to that, also the radiojets show clear asymmetries both in the surface brightness and the morphology, indicating that they have likely decelerated very close to the region where they are launched. And in addition to that, what we observe is that the total source length, so the total length of the radiojet is only 2 kiloparsec. And there is no other evidence for larger scale radio structures. And based on well-known radiojet age size correlations, we can conclude that we are looking at young radiojets, so a young radio source. For all these reasons, this object turned out to be a good case for studying a jet ISM interaction. And indeed, we asked and obtained follow-up Cycle 6 ALMA observations of this object, targeting different molecular transitions. So in addition to the previous CO221, we asked for the CO120 and the CO322 transitions, but also we asked for HNCO and SIO molecular lines and for HCO plus 43. Now, unfortunately, I don't have time to go into the details of the reasons why we asked exactly these lines, but I think it has been highlighted also very well yesterday by in other talks that to investigate, to study the physics of the cold gas is very important to probe it using different various molecular transitions, different molecular lines also. Now,
2 minutes.
Yeah, thank you. Now, the CO gas is very nicely detected. The CO120 and the CO322 are very nicely detected. And here I show the moment 0, 1, and 2 maps in comparison with the previous CO221. And as you can see, especially from the moment 0 map, there are clear differences in their distribution. In particular, the 1 to 0, there is a deficiency of the ground, of the emission from the ground transition in the inner regions, where instead the CO322 is the brightest. And knowing that higher J CO transitions require higher temperatures and density to be excited, the distribution of the CO points toward the presence of higher gas excitation in the central regions. This is confirmed also by the R21 and R31 flux density ratios, showing enhanced line ratios in the region around the radiojets, here overlaid in black contours. And in particular, the ratios that we, the values that we observe indicate an excitation temperature of greater than 550 Kelvin and likely also optically thin conditions. So in conclusion, we can say from these maps, from this analysis, that the jet CO coupling in the central region is strongly altering the gas physics. We also carried out a detailed modeling of the CO322 kinematics, which is interesting because it's the only one among the three transitions extending up to the very center of the gas distribution. And as you can see from the top left map, the observed velocity field seems to be reasonably well reproduced using a model accounting for gas in purely circular motions and accounting for the presence of both a position angle and an inclination warp. Nevertheless, we observe significant residuals in the data minus model map on the top right, with velocities of the order of 90 km per second. And in particular, the residuals along the minor axis are interesting mainly because here the circular velocity component is close to zero. So any residual velocity is likely associated to radial motions. And this can be also clearly seen from the minor axis position velocity diagram showing a velocity gradient up to 200 km per second that is not reproduced by our model overlaid here in Chian contours.
We should finish soon. So 1 minute.
Yeah, it's the last slide.
Okay, perfect. Sorry.
No, sorry. Yeah, just to conclude, as a part check, we also extracted the spectra in the regions where the brightest residual were found, and briefly we found velocity excesses that are compatible with an outflow that is likely jet induced. The interesting thing here is just that the mass outflow rate is very low, and in particular significantly lower than other known cases. And this is, well, a possible explanation for that is related to the jet age, which are in this case more evolved than other known cases. So yeah, I stop here. Sorry.
No problem. Thanks a lot. So I have to admit that I was not so familiar with LERCs, but I have learned today about them. So thanks a lot for that.
No, yeah, I know that's why I used to introduce the the type of objects because yeah,
that was very good. Marcella, so are there some questions from the chat?
Yes, indeed. So first question is related to NGC 3100. So is the CO emission forming a second nuclear ring around the center of the source, or is the jet intersecting with the CO?
I'm not sure I understood the questions, but yeah, well, I think
it is an effect of the projection in your contours towards the colors image. So the effect is that the ring is surrounding the center, or is coplanar to the jets?
No, it's surrounding the center. So at least we think that it is surrounding the center. So yeah.
Another question, it would be great to see not only cold molecular emission, but also whether warm, so UV and hot, so the X-ray emitting gas is residing, and how the jet is influencing the medium.
Oh yeah, that's a comment.
That's a comment, yes.
Yeah.
I have a question, so in case, so unless you want to add something to this comment, but yes, in the last minute. So when you were showing this excess in the residual, so when you were comparing so this is more east-west, let's say, or more horizontal compared to the direction of the jet, right? So the jet is more north-south than this. So can we, so is the jet really doing anything on these features that you observe, or it's not related to?
No, yeah, the thing why, the reason why we think that is related to the jet is that the regions where we observe the residuals are also the regions where we observe the highest line ratios. So where there is likely a high gas excitation. And also, this is a good question actually, mainly because it is foreseen through the simulations that when the jets interact with the surrounding medium on sub-kiloparsec scales, they sort of create cocoons of shocked gas that can be accelerated over a wide range of directions. So it's not, it is possible that we can see outflowing, jet-induced outflowing gas also in this direction, yeah.
Okay, yeah, thanks for the clarification. So thanks again for the talk.